Hi, in this lesson we will study vectors in space. Let's consider the coordinates x, y, z. Rectangular coordinate system. We know that a directed line segment is called a vector. It is indicated which of the ends is the beginning and which one is the end for such a segment. For example, we have a segment AB. It is known that the point B is the end, and then we say that we have a vector AB. Let's mark it with an arrow. Now we'll take a look at definition vectors in space, x, y, z coordinates. Let our point B have coordinates x2, y2, z2, and point A has coordinates x1, y1, z1. Then the vector AB. By the way, the vector is denoted like this, or we can mark it with a small Latin letter. For example, vector A. And this vector symbol can be omitted. It happens very often. You can call it the vector A. Vector A will also have coordinates, and its coordinates are defined as follows. We need to subtract the coordinates of the beginning, that is, the coordinates of the point A, from the coordinates of the end, that is, from the coordinates of point B. That is, the vector A will have such coordinates. The x-coordinate will be x2 minus x1. The y-coordinate will be y2 minus y1. And the z-coordinate will be z2 minus z1. Thus, we can set the vector using three numbers, three coordinates. But note that, for example, it seems to us that this number is, let's say, 3, 2, 1. We can pick an infinite number of points A and B so that the coordinates would be 3, 2, and 1 again, but at the same time, x2 and x1 turned out to be completely different. That is, generally speaking, when we set a vector, we are not talking about one vector, but about the many vectors with the same coordinates. Two vectors, A and B, will be equal if and only if their corresponding coordinates are equal. That is, if the vectors have the same coordinates. Vector A has coordinates x1, y1, z1, and vector B x2, y2, z2. That is, if the coordinates are the same, then we say that these vectors are equal, or in fact, they are the same vector. Let's consider some examples with operations of vectors. Let's have a vector A with coordinates x1, y1, z1, and vector B. Let's omit this symbol in the future. And vector B with coordinates x2, y2, z2. Then we can introduce the concept of the sum of these vectors. You might remember from school that in order to add two vectors, we must first plot one vector. Plot the second vector from its end. Then connect the beginning of the first and the end of the second. We will get the sum of these vectors. A similar concept of the sum of vectors is also introduced in space. If we work with coordinates, then the coordinates of the sum of vectors will be equal to the sum of the corresponding coordinates. So x1 plus x2, y1 plus y2, z1 plus z2. That is, we get a new vector with these coordinates by adding two vectors. The same will happen if we subtract. If there is a minus here, then there will be a minus as well. Minus and minus. In general, if we multiply the vector A by some lambda number, then we get a new vector with coordinates lambda x1, lambda y1, lambda z1. That is, to multiply a number by a vector, we should simply multiply each coordinate by this number. Let me remind you how the multiplication of a vector by a number looks like. If the lambda number is greater than 0, then we get some vector that is co-directed with the vector A, with modulo lambda length A. If the lambda number is less than 0, then we will get an opposite vector. For example, the vector A is like this. If the vector is positive, then lambda A will look like this. If the vector is negative, then it will be oppositely directed. This is expressed through multiplication in coordinates. When a vector has the beginning coincide with the end, then we can call it a null vector. It is designed as 0 with a dash or just 0. And it is obvious that the 0 vector has 0 coordinates. Let's find the length of the vector. Let me remind you that the length of a vector is the length of the corresponding segment. If we have a vector A that has coordinates x, y, and z, then the length of the vector A through the coordinates is calculated as the root of x squared plus y squared plus z squared. Let me remind you of such a concept as the collinearity of the vectors. Vector A is collinear to vector B if they are parallel to the same line, or they just lie on the same straight line. For example, we have such a vector A and such a vector B. They lie on parallel lines, so these vectors are collinear. This is expressed with coordinates as follows. Two vectors will be collinear if their coordinates are proportional. This means that y1 divided by x2 equals y1 divided by y2, and z1 divided by z2. Thus we can determine whether the vector is collinear or not by knowing only their coordinates. By the way, three vectors a, b, and c are called coplanar if they lie in the same plane. Accordingly, if three vectors don't lie in the same plane or are not parallel to the same plane, then such vectors are called non-coplanar. So we have repeated some concepts related to vectors. These concepts have been familiar to us in school. Now let's take a look at some new concepts. A linear combination of vectors a, e is a sum of this kind. Some number lambda e multiplied by a and e, where e is a number from 1 to n. Such a sum is called a linear combination of vectors. If a linear combination of the vectors lambda e, a, e equals the zero vector, if and only if all the numbers lambda e equal 0. That is, this sum can be equal to zero vector only if all the lambda e coefficients are equal to 0. Then we can say that vector a1, a2, and so on, an are linearly independent. If we have such a sum executed with some other set, not the zero set, then these vectors are called linearly dependent. In the space R3, that is, in our three-dimensional space, any four vectors will be linearly dependent, and three vectors can be linearly independent. Three linearly independent vectors in particular, for example, in the space R, namely, three linearly independent vectors e1, e2, e3 from the so-called basis. The basis means that we can express any vector of this space in terms of a linear combination of these vectors. A frequent case of a basis is a basis associated with vectors I, j, k. Let me remind you that we have introduced such vectors. The vector A is a unit vector, that is, the length of which is 1, and which is directed along the x-axis. This is the I vector. The vector J is a similar vector of unit length. It is directed along the y-axis. And vector K is a similar unit vector directed along the z-axis. So, we have vectors I, j, and k. By the way, the coordinates of the vector I will be 1, 0, 0. The vector j has coordinates 0, 1, 0. And the vector k has coordinates 0, 0, 1. These three vectors from the basis. That is, we can express any vector in terms of these three vectors. Actually, when we talk about the coordinates of a vector, we mean exactly the coordinates of the vector in this basis. But we can introduce any other basis and consider the coordinates in this new basis for space. Let's consider an example. So we have vectors e1, e2, e3, and vector a. It is required to prove that the vectors e1, e2, e3 form a basis and express the coordinates of the vector a in this new basis. In order to prove that these three vectors form a basis, we need to prove that these three vectors are linearly independent. The easiest way to do this is as follows. We can consider the determinant. The first line consists of coordinates e1, 2, 2, minus 1, the second respectively 0, 4, 8, and the third minus 1, 3. So, if this determinant is equal to 0, then some rows are linearly dependent. Then these three vectors will be linearly dependent and don't form a basis. If this determinant is not equal to 0, then these three vectors will be linearly independent. Therefore, to prove that these vectors are linearly independent and form a basis, we just need to show that this determinant is not equal to 0. Let's calculate it. We can use different methods, and we can simplify it a bit. For example, add the third row multiplied by 2 to the first row. That is, we add the third line multiplied by 2 to the first line. What will we get? Minus 1 multiplied by 2 is minus 2 plus 2 equals 0. And there will be 0. There will be 6 plus minus 1 equals 5. And we got 0, 0, 5. Let's leave this row as it is. 0, 4, 8. And we leave minus 1, 3 as well. Now we have two zeros in this row. We can decompose it into elements of this line. There will be 0, 0, and 5. Please note we multiply by minus 1 to the power. Looking at the first row, third column, 1 plus 3 is equal 4. That is to the power of 4. And we multiply by what is left after deleting this row and this column. 0, 4, minus 1, minus 1. There will be 1. We consider this determinant. That would be 0 minus 4 would be 4. 4 times 5 equals 20. It's not 0. The determinant is not equal to 0, which means that the vectors are linearly independent, which means that the vectors e1, e2, e3 form a basis. This means that we can express any space vector in terms of a linear combination of these vectors. That is, we can express the vector A as some number lambda 1, e1, plus some number lambda 2, e2, plus some number lambda 3, e3. So these numbers that we need to determine will be the coordinates of the vector A in the basis e1, e2, e3. We just need to calculate these numbers. We can do the following. We can write down the sum by coordinates. The x-coordinate of vector A is equal to 1. Lambda 1 is multiplied by e1. Its x-coordinate is 2. We get 2 lambda 1 plus. Lambda 2 multiplied by e2 is 0. Let's write it down like 0 lambda 2. Next it will be lambda 3. Same thing with y-coordinate. 1, 2 lambda 1. 4 lambda 2 minus lambda 3. And z-coordinate. 2 equals minus lambda 1 plus 8 lambda 2. 2 equals minus lambda 1 plus 8 lambda 2 plus 3 lambda 3. Lambda 1 plus 8 lambda 2 plus 3 lambda 3. We got a system of linear equations for lambda 1, lambda 2, lambda 3. We need to solve this system by any known method. If we solve it correctly, then we get lambda 1 equals 1, lambda 2 equals 0, lambda 3 equals 1. That is, the coordinates of the vector A in the basis e1, e2, e3 will be 1, 0, 1. Please note that in the standard basis, the coordinates turned out to be 1, 1, 2, and in the new basis, the coordinates are completely different. This video lesson is over.